Hello everyone, this is Mr. Underkoffler. Today we're looking at the guide it's called Comparing Probabilities of Simple Events. Alright, so what I've done for you here is I've split up a comparison of relative frequency and experimental probability, and we're going to compare it to theoretical probability so we can understand the differences between the two. Now, similarities. Their two fractions are very close to being exactly the same. Both numerator is the number of times something can occur. Both denominators are the total number of outcomes. The subtle difference is with theoretical probability, your numerator is the number of ways an event should occur. Not how many times it actually occurred, but how many times it should occur. And the denominator, subtle little difference, total number of possible outcomes. Not total number of actual outcomes, but the total number of possible outcomes. So you're starting to notice how I'm wording this. Relative frequency and experimental probability is based on actual results from doing multiple trials of an event. For example, a number cube is rolled 20 times, multiple trials here. So there's 20 total outcomes in the experiment. That is based on somebody actually doing it, somebody's actual results. Now, theoretical probability is based on the outcomes in the sample space, not on actual outcomes from doing trials. For example, let's talk about the number cube again. A number cube is rolled, but we don't care how many times it's rolled. Not for theoretical probability, we don't, because theoretical probability is not based on actual results from doing trials. So we just think about how there's 6 sides to a cube, and therefore there's 6 outcomes theoretically. So notice the difference here. The number of outcomes for experimental probability or relative frequency is based on how many trials you did. But the number of outcomes for theoretical probability is based on the outcomes in the sample space, like 6 sides to a cube, so there's 6 outcomes, or 2 sides to flipping a coin, so there's 2 outcomes. Let's look at another example here. Problems 1 and 2, we're going to use this information for it. A board game is played that contains a stack of cards. The stack of cards has 30 task cards, 15 expense cards, and 5 special cards. Elena randomly selects a card from the stack, records which card she got, and then returns the card to the stack. She repeats these steps 24 times. Her results are shown in the table. Okay. Problem 1 is asking for the relative frequency of selecting a task card. Problem number 2 is asking for the theoretical probability of selecting a task card. Now, how do we do this? We first of all have to decipher which one is the actual results from somebody doing trials. Well, Elena randomly selected a card and repeated this process 24 times. Those results are in the table. So, the actual results of Elena selecting a card at random, those results are in the table, and that's what we're going to have to use for the relative frequency. For theoretical probability, we don't care how many times Elena selected a card. We have to instead care about the sample space. Now, by the sample space, I mean how many things actually exist in this situation. Like back when you were rolling a number cube, there's 6 sides to a cube that exist. So there's 6 total outcomes theoretically. Well, in the game that Elena is playing, the game has certain cards that exist, correct? And that was explained to us right up here. It tells us the card contains the following cards: 30 task cards, 15 expense cards, 5 special cards. This is what the game contains. So whether or not you play the game for an hour or don't play the game at all, these are the cards that are in the game. So whatever is in the sample space, that is what you use for the theoretical probability. But whatever is in the results from doing something multiple times, that is what you use for relative frequency or experimental probability. So let's go ahead and now answer these, now that we know which numbers to use for what. The relative frequency of a task card. Well, I can see the task card was 14 times being drawn, out of a total of 24 times. By the way, if you add these numbers in the table, that would also give you 24. So the easy part, once you know which numbers to use, it's pretty easy. 14 is your numerator. The total number of times that Elena was randomly selecting cards is your denominator. Reduce this. Both these numbers are divisible by 2. That's going to give you 7/12. And then use your calculator. Go ahead and take 7 divided by 12. If you don't already have a calculator out, please hit pause, get your calculator out. 7 divided by 12 should give you 0.583 repeating. Move that decimal point 2 places to the right. And here we go. We got our fraction in simplest form. There it is. And we got our percent. Boom. There it is. Now that's for the relative frequency. And that was based on Elena's actual results that were shown in the table, just like they told us, from her repeating it 24 times. That was the number of trials that she did. Now, theoretical probability is based on, well, just what's in the sample space. In other words, what are the cards in the game? Well, that's told for us up here. 30 task cards are in the game. How many total? Well, go ahead, take 30 plus 15 plus 5, and that'll give you your total. 30 plus 15 is 45, plus 5 is 50, so our denominator is 50, and since we're trying to get the theoretical probability of selecting a task card, 30 task cards, well, that would be your numerator. I like numbers that end with 0. They're pretty easy to reduce. This is just going to divide them both by 10. You get 3/5. You probably already have this one memorized. The 3/5 is 0.6 and therefore 60%. So you probably don't need a calculator for that. But if you did, no harm. 3 divided by 5, you'll get the 0.6. Okay. Now that we did a problem together where we had to figure out who was the actual results from the trials, that was here in this table, what was the sample space, that was the cards in the actual game, whether you play the game or not, these are the cards in that game, so that's what we use for the theoretical probability. Now that we've done that together for a problem, let's have you try one here on your own. So hit pause, read 3 and 4, make sure you read the situation above it as well, and see if you can figure out what numbers you're going to use for your fractions for relative frequency and for theoretical probability of rolling a 2 from the number cube. Okay, hit pause, try this on your own, hit play once you're ready to see how you did. Okay, have you already tried 3 and 4 on your own? Relative frequency uses actual results. The number cube was actually rolled 30 times. 30 trials were done, and those results are in the table. So this table here, that's what we're going to use for relative frequency. And for rolling a 2, the 2 was rolled a frequency of 3 times out of 30. So that's what you should have used. If you botch that up, feel free to hit pause, fix your work, and then hit play and to continue on. For theoretical probability, I don't care how many times the number cube was rolled. Theoretical probability does not use actual trials. Instead, it just uses what's in the sample space for a number cube. A number cube, as you see the little picture I have for it here, has 6 sides. Only 3 of them are showing here from this perspective. But the numbers 3, 5, and 6 would also be on a number cube, as I already had listed in the table. So only one of those sides is a 2. You can see it right here. 1 out of 6 sides is a 2. So that's what we need to use for the theoretical probability, because theoretical probability uses what's in the sample space. Relative frequency and experimental probability, they use actual trials, actual number of times that the experiment was done. And that was 30 times, and those results are in the table. Okay, if you are already good to go, you've already fixed your work, if you had these 2 answers set up wrong, then let's finish this up. 3 out of 30 reduces to 1/10. That is 0.1, also known as 10%. 1 out of 6, if you divide it, you will get 0.16 repeating. Move the decimal point 2 places to the right to get the percent, 16.6 repeating percent. All right, let's turn the page. The next 2 problems that are going to come up here are going to use a phrase called expected probability. Anytime you hear expected probability, that means the probability that is called theoretical probability. Because what is theoretical is what you expect without actually doing it on your own. Whereas actual probability is based on actual results, which would be your relative frequency. So with that in mind, let's try number 5 together. A coin is flipped 80 times and lands on tails 36 times. What is the difference between the expected probability percentage and the relative frequency percentage of getting tails? Okay, so they are specifying that they want percentages here, and we need to find the difference between. Hopefully you guys remember that the phrase difference between in a math class is subtraction. So what do I need to subtract? I need to subtract the expected probability percentage, which is theoretical probability percentage, because that's what expected probability means, and I have to subtract the relative frequency percentage. Well, I hope you know the relative frequency was already given to us. Well, the numbers we need for relative frequency are given here at the very beginning. They tell us that 80 times this coin was flipped. That's what we're going to use for relative frequency. And it was giving us tails 36 times. So let's go ahead and set this up. 36 out of 80, I can divide that to get the decimal and then make that a percent. If you're wondering why I didn't reduce the fraction, it's because I didn't really have to. The directions here are asking me to find the difference, which is subtraction, between the percentages for expected probability and the relative frequency. All right, for the expected probability, you probably already know this. What should theoretically be the percentage chance of getting tails? Well, you're probably thinking 50%, because there's one side that's tails out of two sides. Expected probability is theoretical, and theoretical uses what's in the sample space. There's two sides to a coin. That's the sample space. All right, so we got our percentages now. We got the theoretical, and that needs to be first. Expected probability was what they mentioned first, and then the relative frequency. So let's go ahead and subtract them. This is really easy subtraction. 5% difference between the expected probability and the relative frequency. All right, I would like for you to try number 6 on your own. It's similar to what we did on number 5, except now we're talking about a spinner with 8 spaces. And I would also then like for you to try 7 and 8. It's kind of similar to what we saw on the first page with 1, 2, and 3 and 4, but it's good for you to try another one here on your own. And it has a problem number 9 that goes with it as well. So hit pause, take your time. I want you to do 6, I want you to do 7, 8, and 9 on your own, and then hit play once you're ready to see how you did. Okay, have you already done number 6, 7, 8, and 9? If you have not, I need you to hit pause now to make sure you are practicing this on your own. That is part of learning math. All right, this time they switched the order on the wording. They still said difference between, but this time they asked for the relative frequency first and then the expected probability. So the order of your subtraction will be backwards from what it was on problem number 5. They told us that the spinner is being spun 45 times and is landing on the 7 9 times. So 9 times we got a 7 for the relative frequency out of 45. If you divide that, you will get 0.2, which is 20%. For the expected probability percentage of getting a 7, there is only one 7 out of 8 equal size spaces. So the sample space is 8 spaces. One of them is a 7. That is your theoretical probability, also known as the expected probability. Divide that, you will get 0.125, which is 12.5%. And now we can go ahead and subtract 7.5% difference between the relative frequency percentage and the expected probability percentage. And finally, 7, 8, and 9. Did you figure out that experimental probability is the same type of thing as relative frequency, except you're talking about what's going to happen in the future? So notice the wording. The experimental probability that the movie he'll watch the next day. So after he's already done the 30 days in a row, the next day, what's the experimental probability based on his results? Well, his results, as we were told right here, were shown in the table. And that's what we need to use for experimental probability, just like relative frequency. Actual results. And we can see here, 7 times. It was a comedy. That was out of 30 days in a row. So 7 out of 30 is your fraction, giving you 0.23 repeating, which is 23.3 repeating percent. For the theoretical probability, we don't care how many days he did it. Theoretical probability cares about what's in the sample space. And the sample space would be what's actually in his collection. And they tell us that right here at the beginning. His collection had 12 comedies, 22 action movies, and 10 sci-fi movies. If you add those numbers together, you will get the total number of movies in his collection, which is 44 movies, and the theoretical probability that he would select a comedy movie at random would be, well, there was 12 comedy movies, so that's 12 out of 44. Reduce that. Both numbers are divisible by 4. That'll give you 3/11. Divide that in your calculator, 0.2727. The 27 goes on forever. So 27.27 repeating. We finally have a percentage where there's 2 digits repeating in the decimal portion of it instead of just 1. There you go. And finally, problem number 9. Which genre was the relative frequency the same as the theoretical probability? Well, I don't know if you noticed this, but if there was 30 days and 15 of them were action movies, 15 out of 30 is, not that one, this one. 15 out of 30 is 1/2, and there was another one that was 1/2 from the collection. Well, it's the same thing, it's the action movies, because 22 out of the 44 total movies is 1/2. So that was one where the relative frequency was actually the exact same thing as the theoretical probability. All right, the last thing we're going to do on these guided notes is set up a scenario for you where 2 people actually do actual results, which is relative frequency, and then we're going to show you their graphs without even showing you their data. And you're going to have to think about which graph is what we would expect based on thinking of the sample space, the theoretical probability. Which graph is what we would expect for that scenario. Okay, so let me go ahead and do one of these with you. The first one. Follow along with me. A tetrahedron is a 3D figure with 4 equally likely outcomes, 1 through 4, identified by the number showing at the top vertex. Ladies and gentlemen, I had that drawn for you right here. That's a tetrahedron. The number on top is what you're getting whenever you roll it. That shows you what you got. Okay, Maribel tosses the tetrahedron, shown 50 times. While Dalton instead spins this spinner right here, shown 50 times. Each student records the results in a frequency bar graph. However, neither Maribel nor Dalton wrote their name on their graph. Okay. So, above each graph, you're going to have to write the name of the student whose graph best represents the results that can be expected from the experiment. Now, you might be like, how in the world am I going to do that? We got these 2 graphs. How am I supposed to know which one it would be Maribel's from the tetrahedron, and how would I know which one is Dalton's from spinning the spinner? Well, pencils in your hand, I'll show you how you would think this through. The tetrahedron, each outcome is equally likely. The same thing would be true if you were rolling a number cube. Every side of the 6 sides of a number cube are equally likely to show up, just like when you're flipping a coin. Every time you flip a coin, it's 50-50. Equally likely to get tails or to get heads. So the same thing is true with this tetrahedron. If I roll this, I'm equally likely to get a 1 as I am to get a 2, as I am to get a 3, as I am to get a 4. Equally likely. One of these graphs shows you something close to the results being equally likely. More on that soon. But with the spinner, look at this spinner. Do you see what I see? Do you see how the 4 and the 3 are much bigger spaces than the 1 and than the 2? Well, write this down. Therefore, the 3 and 4, the outcomes for 3 and 4 should be greater than the outcomes of getting a 1 or a 2. So, with that in mind, can you find the graph where getting a 3 or a 4 is going to have a lot more outcomes than getting a 1 or a 2? Oh, I think we just pretty much made it clear, didn't we? This graph right here is the one that matches that spinner. And if you go back to the paragraph, it told you Dalton is the one who spun the spinner. So Dalton's graph must be this one, where you don't get a 1 or a 2 very often because those spaces are small. 3 and 4 are big, which is why we got a 3 or a 4 a lot more often. However, Maribel's tetrahedron, now she only did it 50 times. So the results were not perfectly equally likely to each other. The 2 was a little lower than you would have expected, but it's much closer to being equally likely than what this one is over here on the left. Okay, now that I've led you through that, let's have you try to on your own. Problem number 11, we got 2 different spinners involved, and then problem number 12, instead of having any pictures at all, they're just describing to you what was used in their experiment, and you're going to have to figure out which graph A or graph B, is Caleb's and which one is Joel's. All right, so hit pause in the video, try 11 and 12 on your own, and then hit play once you're ready to see how you did. Okay, problem number 11. I'm assuming you already did this on your own. Did you notice Jaden's spinner is very interesting? The 1 and the 2 are super small spaces. So their outcomes should be considerably less than the outcomes for the 3, the 4, the 5, and the 6. Well, looking at the graph, well, here it is. It's got to be this one right here. That one, the 1 and the 2 didn't happen very often, but the other numbers happen a lot more often. With Nikhil's spinner, it's much more evenly spread out. The 1, the 2, the 3, the 4, the 5, and the 6, they should all be equally likely to each other. Now, it's not going to be perfect when you only do it 50 times, but it's close to what you would expect for the theoretical probability of each of these results. By the way, I forgot to mention this, but at the bottom of the previous graph, it does point out that the second graph, the results are more evenly distributed across each possible outcome, and that's the idea of being equally likely to each other. All right, problem number 12. Caleb's experiment, the number cube is 1 through 6. Each of those outcomes should be equally likely to each other. But with Joel's experiment, there are 6 cards labeled 1, but only 2 cards labeled a 2, and 3 cards labeled a 3. And check this out. This one we should pay attention to. Only 1 card was labeled a 5, so that one should be really low. And only 2 cards labeled 2. The 2 and the 5 should be very low when compared to the others. And you know what? The 3 should be kind of low as well, but not as low as the 5 and the 2. And the 1, we should have a lot of 1s because there were 6 cards labeled 1 and 5 cards labeled 4. So did you figure out which one is showing the 1 showing up more often and the 4 showing up more often, but the 2 not showing up very often at all? Boom, it's graph B. Hopefully you can see that. Graph A is more evenly distributed. Graph B, the 2 and the 5 are pretty low. The 1 and the 4 are pretty high. Well, that's what we would expect here, since the 1 had more cards and the 4 had more cards versus the other ones. So that should be, what was the name of that person? Oh, yeah, Joel. That should be Joel's result. So graph B should be Joel. Caleb's, each number on the number cube should be equally likely to each other. And that's shown here on this graph. They're more evenly distributed across each outcome. So graph A for Caleb. And that concludes our guided notes on comparing probabilities to simple events. Thank you for watching. We'll see you next time.